Alright, ladies and gentlemen, welcome back. Today we're going to be talking about inverse functions and how to define them. Okay. So, what we're going to take a look at is something called an inverse function. And basically, functions f and g are inverse of each other provided that, well, first off, slow down a little bit. When you guys see written f of g of x, okay, and g of f of x, we call this the composition. Okay. So this is what we did yesterday. You're taking the composition of both functions, okay, and they must equal out to be x. So now we're talking about notation for inverses as well. You're going to see me write down f raised to -1 power, and we call this f inverse. Okay. So let's see here, finding some inverses algebraically. It's actually a very easy process. If we're trying to find the inverse of, say, y equals 2x minus 4. First thing you're going to do is you're going to switch your x and y, and all you're going to do is wherever the x was you put a y, wherever the y was you put an x. So x equals 2y minus 4, and then you solve for it. So let's see here, we added 4 over, so divide everything by 2, bam. I would accept either this, okay, or x plus 4 over 2. Both are acceptable answers, okay? And then what we do is we write out our inverse, f inverse of x, boom, done. So please watch how simple this is. We have an example over here, find the inverse of y equals 3x plus 5. I'm going to switch the x and y around. So x equals 3y plus 5. Okay. And now we're trying to solve for y. I'm going to subtract 5 from both sides. So 3y equals x minus 5. Hopefully you guys are okay with me moving the y over there. And I'm going to divide everything by 3. So y equals x minus 5 over 3. Or you could also see it as 1/3 x minus 5. Either one's fine. So use proper notation. I'm going to write down f inverse of x equals. I'm going to write this one out as x minus 5. The whole quantity divided by 3. Okay? Very good. So, alright, obviously they get a little trickier. Here, it's same idea, y equals x squared plus 1. So, the x and the y switch. Now notice that the y becomes y squared since it was an x squared. Again, I'm solving for x and solving for y. So I subtract 1 over, I square root both sides, and then when you square root, you take the absolute value of both sides, that's why I have the plus or minus there. So my inverse is plus or minus x minus the square root of x minus 1. Now, what's the thing that you notice from here to here? This isn't a squared, this is a cube, okay? So I'm going to switch the x and y around. X equals y cubed minus 7. All right, and now I'm going to solve for y. So I'm going to go ahead and add 7 over. Okay, and then I'm going to cube root left and cube root right. Okay, so in doing so, what I've got here, this becomes y equals, and I leave it the cube root of x plus 7. Do I need a plus or minus out front for cube root? Hopefully you guys are okay with no. You only do that for even powered roots. Down here, I have f inverse of x equals the cube root of x plus 7. Okay, very nice. So, on to the back. Very good. Okay, so here, verify. Now, this is a little more complicated. This actually kind of builds off what we did yesterday. Verifying that two functions are inverses. To verify that f of x and g of x are inverse functions, we must take the composition of both. So, yesterday we talked about inputting g function into the f. So, see how it says 2 times something? Well, it's 2 times this new something is that, minus 4. And it has to equal x, must equal x. And you're going to notice that for both of these, they do in fact equal x. All right, if they do, bam, they're functions, or sorry, they're inverse of each other. All right, so let's take a look over here. I'm trying to see if they are or are not inverse functions. So I'm going to do f of g of x first. So f function says something minus 7. Okay, that's my f function, something minus 7. The something that I'm going to put in there is this g of x. Okay, so x plus 7 minus 7. Well, if I do that, it does indeed equal x. Sweet, that's what I want, winning. Over here, g of f of x. Okay, so I go, my g function is something plus 7. Okay, well, the something that I'm going to put in there is my f function, so it's x minus 7 plus 7. They cancel out. I get x's. So my explanation, because f of g of x and g of f of x equal x, f of x and g of x are inverses. Okay, that's a really bad inverse. Okay, wonderful. Finally down here, there is also a quick test that we can use in order to prove that we have an inverse. Okay, so if no horizontal line intersects the graph of a function f more than once, then f inverse of x is a function. We call this the horizontal line test. You guys seem to remember vertical line test. So this is just another example. Is the inverse of example 3 a function? All right. So what we're going to do here is take a look at example 3. Okay. And I'm going to graph x squared plus 1. Okay. Now the beauty of this horizontal line test is the fact that I'm only graphing the original thing. Okay, so y equals x squared plus 1. I'm going to hit graph. Now, it's called the horizontal line test. Normally, you do what we call a vertical line test, where you go straight up and down and you go left to right. So this function originally is a function. Sorry, this graph originally is a function. But the horizontal line test is when I take my pen and turn it horizontal, go up and down, you'll notice it's more than one point. Since it does, we can now say that the inverse is not a function. The inverse is not a function because the original, man, I cannot write today. My apologies. The original graph failed the horizontal line test. Okay. Very good. Awesome. Okay, so then finally, example 8 down here. If f of x equals 1/2 x cubed minus 2, find the inverse and determine whether the inverse is a function. Well, okay, what we're going to do first is, since I already have my graphing calculator right here, I'm going to put this in. I'm going to hit y equals. Okay, I'm going to do 1/2 x cubed minus 2. I'm going to hit graph. And I'm blowing up right now. Sorry, I'm just Mr. Popular over here. So we can see that our graph looks good. Okay, if I do the horizontal line test, it passes because it only ever hits the graph one time. So is the inverse a function? Yes. F inverse, okay, is a function because it passes the horizontal line test. Okay, so you're all good there. But now let's find it. So hopefully you guys are all cool with this too. When this says f of x, we can replace that with y equals. All right, so 1/2 x cubed minus 2. I'm going to replace the x and the y like we did in the front. So x equals 1/2 y cubed minus 2. I'm going to add 2 over. X plus 2 equals 1/2 y cubed. All right. Now, think about what's next here. Pardon me. The opposite of dividing by 2 is to multiply everything by 2. So that'll cancel out the 1/2 on this side. And over here, I'm going to get 2x plus 4. I still have y cubed. Sorry, I always like my y on my right left side. It's just bad habits, or good habits actually. So then to get rid of that cube power, I'm going to cube root left, I'm going to cube root right, so y equals the cubed root of 2x plus 4. And finally, I want to replace that y with f inverse of x equals the cube root 2x plus 4. And we win. Okay. Just one last little thing, just because I thought it was kind of interesting. If you take a look at any of these graphs, okay, so I'm going to come over here real quick to the original one. Find the inverse of blah blah blah. Now, if you hit y equals on here, I'm trying to get the best you can actually see. There we go. All right. If you go to y equals and you type in the original graph, 3x plus 5. Okay. And then down here, this is my inverse function that we found for the first example, x minus 5 divided by 3. And if I hit graph, okay, interestingly enough, every inverse functions of one another will be symmetric about the line y equals x. So if I graph the line y equals x, you're going to see that everything, they'll always meet the same points, and they are basically symmetric. They float right over top of it. Okay, and that goes for every graph down. All right, the only time you're going to see something a little bit goofy is here, because of particularly domains and so on. But all good. So as always, guys, keep the good work. Thank you for paying attention, and good luck. We're all counting on you.